Now I couldn't help myself. I just went to Excel, just took a minute to put the data in and so forth. And somewhat shockingly, the velocity model, the best fit for this line, turns out to have been 0.102 t plus 0.49, almost exactly the same as the model I looked into here. The model for the, for the quadratic data here, the data was supposed to be quadratic, the best fit quadratic turned out to be not 0.07 t squared plus 28, but essentially 0.05 t squared plus 0.45 t plus 29. Okay, so I wasn't very close with that model. And the flaw is that I seem to have assumed that the model would be horizontal, the vertex would be on the y-axis, when it really wasn't, and that's probably due to some delay in my counting or something. You don't have to worry about the details of that, but those are the kind of things you want to think about when you're modeling actual data. Also, the models fit quite well. The residuals for the best fit quadratic were all less than 1. And the residuals for the velocity data, well, as you see, the velocity information was more scattered. So the residuals are fairly significant, but despite that, we got this. And if you know calculus, you know that the derivative of 0.0501 t squared is 0.102 t. Matches precisely to 3 significant figures. Now, that's just luck. The derivative of 0.5 t is 0.45 t is 0.45, not 0.49, so we don't want to get too big of a head here. But it shows that despite the crude way I obtained the data by my count and obvious errors, systematic errors that would occur in that system, by the time we smooth out all our data, we get extremely good results. And it probably wouldn't be that good if we were to repeat the experiment. But I do believe if it's done carefully, we would always get pretty good results. We tend to get pretty good results from that sort of experiment. Of course, we can improve on those results, but you know, with more accurate timing methods. But this is pretty astounding agreement here. And I'll just add the comment that your graphing calculators are just as capable of producing these best fit models. They're set up to do that. They do a nice job of it. They do it just as accurately as Excel. So if you put this information into your calculator and did the best fit models, you get the same results that we got here if you use the same data. And your text discusses how to do that. You're not going to be tested on whether you can do that in class, because I would rather have you estimate the model, because it gets the idea into your head much better. And once you understand how the curve fitting works, and the linear curve fits and the quadratic curve fits and so forth, and when to use those, it's very easy to learn to do it on your calculator. I prefer that you learn to do it by hand graphing, because you simply learn it better. But then once you have the idea, the graphing calculator is a wonderful tool. And that sort of is consistent with my fairly strong belief that you need to learn the mathematics without a calculator. You simply need to learn the mathematics, and then the calculator just proves to be a really handy tool for doing the mathematics you already know how to do, rather than for pretending to be able to do the mathematics that you don't understand and that you don't really relate to. So relate to the mathematics on pencil and paper, relate to the mathematics in the real world, save the graphing calculator for after you understand the mathematics. And that will be the approach in this course.